Hello everyone, welcome to Chapter 4, Applications of Derivatives, and we focus on antiderivatives. As the name suggests, anti is opposite or reverse, and derivatives is the process of finding the differentiation. So we know how to do the derivatives. We have shortcuts. So we know that if we are given a function f of x, from that we can find the derivative f prime of x. Now antiderivatives is the reverse process. That means we will be given this f prime of x, and we should be able to find the function for which this is the derivative. Okay. Now remember again, the reverse process is to help us recover the function. Okay. So for that, what we do is we try to find this f of x. However, when we are given problems, we will not be using these notations f of x and f prime of x. Okay. Instead, the problem will give you f of x, which is the derivative, because here the function is this. And when they ask you to find the function whose derivative is f of x, then we have to use another notation, and we usually use capital F of x. Okay, where this small f of x in this antiderivative condition would already be the derivative. Okay, so I want to write that information here. So let's say you had this problem where they asked you to find the antiderivative. So if you read this problem, it says find the antiderivative for each of the following functions, and we're looking at problem number 1. F of x equals 2x. Now if you looked at just the way it is presented, you know it's f of x, they didn't say f prime of x. However, our hint comes from the language here. It says antiderivative, find the antiderivative. Therefore we know that what they're giving us is already the derivative. So this, for us, we should remember that. The given function f of x is not a regular f of x. Regular meaning the usual function from which we find the derivative. Rather, this function is already in the derivative form, right? It's already in f prime of x form. So we need to think backwards. So what function should I have so that its derivative will give me 2x? So you have to do it all in reverse. It's like rewinding those steps. So for that, we want to see what could give us the 2x. The 2x will come in when the 2 was in the power, right? So that you bring down the 2 and then you reduce the power by 1, that's where you get the 2x. So we see that capital F of x, meaning the antiderivative, should be x squared, so that f of x is 2x. So I want to quickly point out to you that this one is the antiderivative because it's a capital F. This is a notation that I'm bringing in to differentiate between the two f's, and this is already the derivative. So in this case, antiderivative would take us back to the original function. So we are recovering the function, which is x squared, for which it's 2x. But wait, what if my f of x was x squared, say, plus 1? This means its derivative, which is f of x in this case, would also be 2x, isn't it? So what if my f of x was x squared minus 7? That also will come back as 2x. So what I notice is if it's not just x squared, but it's x squared plus any constant, and when I say constant, it could be positive, negative, fraction, decimals, irrational numbers, anything. So I have to generalize this, and so say to keep it arbitrary, we use an arbitrary constant c. So capital F of x should be then x squared plus c. C could be negative, right? So the plus c is like a generalized version of it. And so that is really helpful here. Let's take a look at the next problem. G of x equals cosine x. So its corresponding antiderivative will be capital G of x. So what, when taking the derivative, would give us cosine x? So here again we think of sine x. So G of x must be sine x. We're thinking backwards. Can we, okay, just say, which implies small g of x. Derivative of sine x is cosine x. What about g of x with a constant? Plus 3. That also will give us g of x to be cosine x. So using the same argument, it implies that g of x must be sine x plus some constant c. The theorem says if f is an antiderivative of small f on an interval I, the most general antiderivative of f on I is f of x plus c, what we just saw. So here's another problem. Find an antiderivative. Notice the language, an antiderivative of f of x equals 3x squared that satisfies f of 1 equals negative 1. Now we have f of x to be given as 3x squared, and this is the derivative. So we have to think backwards. If you bring the 3 back up here, what do I get? If I brought the 3 back here, that will make it a 6, right? 3 times 2, x power 6. That's not what we want. So you have to think differently. How do I get 3x squared? So yes, I have to take the 3 back, but I will not multiply it to the 2. I'll have to assume that there was no 2. So capital F of x will be x cubed. Yeah. So when I say backwards, sometimes I've seen students do that. They take it back and they multiply it with the existing number. But remember, it is as if that number wasn't there. So it's x cubed, and now try to test it. So if you took the derivative of x cubed, that will be 3x squared. Yes, now that matches. So we have we are given f of x equals 3x squared, which is already the derivative. So think backwards and see what will give us 3x squared. So capital F of x, if it was x cubed, this 3 is your hint, isn't it? So if it's x cubed, then if you took the derivative, which is, you always test it, okay? When you determine what the antiderivative could be, test it and you'll see you get 3x squared. But we know from the theorem that you have to throw in the c, so plus c. So this is the most general antiderivative, which means as you keep changing your c, you can generate basically infinite possibilities for capital F of x. Therefore, the question's language, find an antiderivative, says you want to find a specific f of x, a unique f of x. And for that, they gave us this extra hint. They said that satisfies f of 1 equals negative 1. So this means in my given function, the one that I just found, if I plug in f as, x as 1, then it's 1 cubed plus c, and we're told this is equal to negative 1. And this we're going to use to solve for c. 1 plus c equals negative 1, which implies c equals, subtract 1 on both sides, so you get negative 2. So coming back to f of x, we have x cubed plus c, and c is negative 2. So plus c is this. And so f of x is x cubed minus 2. So this is the specific antiderivative that satisfies f of 1 equals negative 1. find the antiderivative of f of x equals 2 minus 5 over x squared, and they want us to check by differentiation. Okay. Again, this is all guesswork, isn't it? So I'm thinking, well, if I got back just the 2 after differentiation, that means there was probably a 2x. So derivative of 2x will be 2. So this is again a guesswork there. Okay. This minus 5 over x squared, again, we've done these kind of problems, therefore it's kind of easy for us to determine it. If not, it's going to be challenging. So if I see this as a negative 2, this would have happened if there was a 5x power negative 1. So that the negative 1 comes down, and then you minus 1 from it, and that gives you the minus 2. So based on that, I know that this is going to be plus 5x power negative 1, and we can rewrite that as 2x plus 5 over x. As always, there will be a c, so let's do that. F of x then would be 2x plus 5 over x plus c. And then we want to do the check by differentiation. So take your f of x, which is this, what we just found, and then you find its derivative, f prime of x, which is nothing but your small f of x, right? The very one that we were given. And that's going to be 2 minus 5 x power negative 2, which will become x squared, and plus 0, which is 2 minus 5 into x squared, and then check this, check proofs. This is the same as your f of x in the given problem. We just saw, particularly in this minus 5 over x squared, how difficult it was to actually reimagine that and see it as x power negative 2, and from there to think backwards and get that 5x power negative 1. And to overcome all these challenges and to remove guesswork from this, we do have a set of formulas that we're thankful for. So we have antiderivative formulas here, and it helps us to put all these things in a formula wherein you have all the bases covered. So technically, if you had x power n as your function, then the antiderivative to recover the original function would be 1 over n plus 1 x power n plus 1 plus c. There's a plus c in all of these. So then you can think of x power negative 2, right? We were trying to find its antiderivative. Forget about the 5. We had the 5x power negative 2. In fact, let me go back. Was it a negative? Yeah, negative 5x power negative 2. So we have the negative 5. So we will tag the negative 5, but then x power negative 2, it says 1 over negative 2 plus 1 x power negative 2 plus 1. That is what we will do to find the derivative. I mean the antiderivative. 1 over negative 1 x power negative 1, which is negative 5 times negative x power negative 1, which is multiply them, so the minuses become plus 5x power negative 1, which was 5 over x. And that's what we guessed, but it was something we saw before in other problems previously, and it helped us that way. But if we didn't see that, then this is super helpful, because you get the same thing but in a very structured manner. Okay. So coming back here, well, we have formulas for all of these. Okay. Take a moment, you can pause the video at this time and look at this more deeply. You can copy it down in your notes. That way we can have them handy. Let's do some problems now based on this. Find the general antiderivative. We have f of x equals x power 5. Remember, this is already the derivative. So this implies we find capital F of x, and we're going to use the formula. And quick recall, x power n, for it the antiderivative was 1 over n plus 1 x power n plus 1. Remember, we did the n minus 1 and we brought it down, but here we bring it down to the denominator because you take the flip of everything, so it's a reverse process. So 1 over 5 plus 1 x power 5 plus 1, which is 1 over 6 x power 6. Because they said general antiderivative, we do the plus c. It's given as part of the formula as well, so we remember that. Problem number 2. G of x equals square root of x. So before we begin the problem, we want to rewrite this square root of x as x power half. In this case, your k is half. If you're using the formula uses k or n. Capital G of x will be 1 over half plus 1 x power half plus 1. So a little algebra here. 3 over 2 x power 3 over 2. Again, clean that up. You get 2 over 3 x power 3 over 2. Of course, a plus c. Don't forget that. Third problem is h of x equals sine 2x. So we have the formula for sine kx. Let me take you there. Sine kx, and the k in our case is 2 because it's sine 2x. It says negative 1 over k cosine kx plus c. We use that here. K is 2. So capital H of x would then be negative 1 over k cosine kx, so cosine 2x plus c. Very, very convenient there. Plus. I of x is cosine x over 2. Here's the case where k is half. So capital I of x will be, take you back to the formula quickly because this is to do with cosine. Cosine kx doesn't have the minus, so it's 1 over k sine kx plus c. 1 over k, which k itself is half, sine half times x kx plus c. Clean this up, this goes on top, so it becomes a 2 sine x over 2 plus c. Next we have antiderivative linearity rules, and this says we can use the sum or difference rule freely, and we also have the constant multiple rule where we pull out the constant and just find the antiderivative of the given function. And as always, we add in a c for general antiderivative. If we are given some initial information, like in one of the problems where we found the constant, then we can go back and give a specific c value which we can find. Until then, if they say find the general antiderivative, please add a c to it. Find the general antiderivative of f of x equals 3 root x plus sine 2x. So before I begin to find the antiderivative, I'd like to rewrite this in a format that's going to be convenient for me to apply those rules, those formulas we saw. So here I have the square root written as power half, and so my n is half, and in this case it's a sine kx, and in this case the k is 2. This helps me for substitution purposes. So the constant multiple rule, as you see here above, says you can pull out the constant and only work on the x power half. So that will be 1 over half plus 1 x power half plus 1. Okay, I pulled out the constant there. And here it is, the k is 2. The formula says negative 1 over k, so negative 1 over 2 cosine kx. K is 2. And then there's a plus c. 1 over 3 over 2 x power 2x plus c. If you clean this up here, this denominator 3 over 2 will become 2 over 3. This 3 and that 3 will cancel off, so we'll be left with 2x power 3 over 2 minus cosine 2x all over 2 plus c. This is a crisp way of writing them, but you can also write them as the coefficient separate from the cosine, no problem. So this would be our capital F of x, which is the general antiderivative. Same thing, find the general antiderivative of f of x equals pi cosine pi x. Is what we have. So capital F of x will be, pi is a constant, so we're only working on the cosine x, and this is a case where k is pi. It's a number, right? K is a constant. It's a non-zero constant. It can't be 0, but it can be anything else. So k is pi here. 1 over cosine has 1 over k, so 1 over pi sine kx, so sine pi x plus c. Again, the pi's will cancel each other, so that gives us sine pi x plus c. This looks interesting, so we'll do one more. If I have g of x to be pi over 2 cosine pi over 2x. So capital G of x will be, I'll pull out the pi over 2 because it's a constant and focus on the cosine. The k here is pi over 2. That's coming from here, okay, not the other pi over 2. Okay, so it's 1 over pi over 2 sine kx, so pi over 2x. That thing is done, and then you add a c at the end, plus c. So that's pi over 2. This will become 2 over pi sine pi x over 2. Let's see, the pi's and the 2's will cancel each other, leaving us with sine pi x over 2 plus c. How about this one? H of x is cosine pi over 2x over 2 is yeah, that's better, plus pi cosine x. Please pause the video, catch your answer, come back and check. Here k is 1, so you don't see much effect there. That simplifies as 2 over pi. Oh, by the way, this is capital H of x. Capital H of x is 2 over pi. Plus c. Alright, so we kind of you should be feeling confident now about these problems, and how our formulas are going to be very helpful in the upcoming sections where we can find the antiderivative quite easily. The next portion here is to deal with initial value problems and differential equations. Now, as the name says, initial value problems, we need an initial value sometimes to solve these problems, and that involves differential equation. Now, we've seen this notation before. It says dy over dx. Right? This is the derivative. So we are basically trying to find an antiderivative for a function which is the same as this, right? This is the same as f of x, and it's for this function that we're trying to find the antiderivative. Okay? And so this is known as the differential equation. And here, if we have an initial value, initial information and preliminary information given to us, then this will help us to go from a general solution to a particular solution. We've seen that in math, but its applications are really profound in sciences, where we can use the initial value to convert a generalized answer to a particular solution. So this means that, you know, we have some real-world problems that start off with an initial condition. So it's based on that condition that we will adjust this. So, you know, a very simplistic way of explaining an example could be a person's medical condition based on, now we have this medication that is in general, so it's like the plus C. So if we have a patient with an initial condition, a medical condition, it's based on that condition that you will adjust the dosage of that medication so that it is particular or specific to that individual patient. So that's the kind of approach that we would like to use when we apply differential equations and initial value to find a particular solution. They solve the initial value problem. Problems. We'll just do a couple of them. So we say we have the first one given to be dy over dx is equal to 2x minus 7, and the initial value for us is y of 2 equals 0. This is very, very similar to the one we did previously. If you recall, we said capital F of 1 is equal to negative 1, and we found the c. So it's a similar approach. We're basically finding the c to give a specific equation. Alright, so we have to find from here, we're trying to find y. So then this will be 2 times, so basically you're trying to find the antiderivative. So the power is 1. It helps. Let's say here n is 1. So 1 over 1 plus 1, x power 1 plus 1. I pulled out the constant, right? Then 7, and here it's as if your n was 0. So if you think of n as 0 here, so it's x power 0. So it's n is 0. Think of it like that. It will be 1 over 0 plus 1, x power 0 plus 1, plus the c. 2 times 1 over 2 x squared minus 7 times 1 over 1 x power 1 plus c. I'm just writing it out just so you can see. The 2's cancel off, leaving us with x squared minus 7x plus c. Yeah. And then this is your y, but you have that plus c, which is a general solution. But remember, initial value will help you to move from a general solution to a particular solution. And we use the differential equation to actually get the y. So we have kind of moved away from the capital F and the small f, and we're going back to familiar information, which is where you're given the derivative and you're asked to find the function. And this notation really makes it visible there, right? Okay, where an initial value says y of 2 is equal to 0, which means the 2, I'll put it in different color. This simply means that this is your x and this is your y. So go ahead and plug that in this equation. So y is 0 equals 2 squared minus 7 times 2 plus c, all this to find c. Okay. So do the math there, and just put these 3 dots to show that you did some algebra to get the c. So your c comes out to be 10. Now you go back and say, okay, we found the y, and that is x squared minus 7x plus 10 as the specific answer for the given initial condition. So this could be our second question, and here we have dy over dx given to be 9x squared minus 4x plus 5, and the condition is y of negative 1 equals 0. So taking the derivative, the antiderivative, that becomes a y, and then this is 9 times, that is n is 2, n is 1, n is 0. Think of it as x power 0, because anything power 0 is 1, right? X power 0. plus c. Clean all this up. So we get the 9 times 1 over 3x cubed minus 4 times 1 over 2x squared plus 5 times x plus c. All these will cross cancel, isn't it? I'm sorry, 3 times 3. That's 2. That comes out as 3x cubed. So y is 3x cubed minus 2x squared plus 5x plus c. Alright, now we have our initial condition, our initial value was y of negative 1 equals 0. So always identify your x and your y. Plug those in. 0 equals 3 times negative 1 cubed. After some algebra, c comes out to be just a 10. Okay, something to do with a 10, but these questions have the c as 10. Here is a word problem. A hot air balloon ascending at the rate of 12 feet per second is at a height 80 feet above the ground when a package is dropped. How long does it take the package to reach the ground? We have the figure here to help us throw in all the details that is given in the problem. Okay, the hot air balloon is ascending, so that means it's climbing up at the rate of 12 feet per second and is at a height of 80 feet above the ground when the package is dropped. So the balloon is going up, the package is falling down. So the question is, how long does it take the package to reach the ground? Alright, now we have a physics problem technically. So we can think of the position, the velocity and all that, right? So what we see here is feet per second tells you that it is velocity, right? Distance over time. So it's feet per second. Therefore the x-axis will be, the ground will be the x-axis, which is t-axis measured in seconds, and the y-axis will be the s-axis, it's s of t, which is measured in feet because that's the height. S of t denotes the height of the package above the ground. The whole problem is about how long it takes the package to reach the ground. So we're not particular about the balloon itself, it is the package that's falling to the ground. But we're interested in the balloon just because they gave us information on the speed of the balloon, so that's coming up next. We want to consider v of t, velocity, right? It denotes the velocity of the package. At time t, because it's v of t. Now there is also indirect information, which is the velocity, the acceleration due to gravity. We know that that's like a fixed, it's a constant. So I'll just write that here. Acceleration due to gravity. It's always fixed, and it is negative 32 feet per second squared. It's the acceleration, so it's a of t, because it's the gravity. So we actually can write it as 32 feet per second because we're already saying it's due to gravity, so it's 32 feet per second squared. So because negative, we always throw in the negative when we do write it as, say, dv over dt. Okay. Because that is nothing but your acceleration, isn't it? Acceleration is the derivative of the velocity, And when I write it like this, then I put it as negative 32 because I cannot put it in words due to gravity, right? So negative because gravity acts in the direction of the decreasing height. So then if I were to denote the decreasing height, I would say, this dv over dt is negative 32, acceleration due to gravity. That's what's happening here. And say this is the package, this pink one. This would be the S of t. It's not picking up. I'll write this out. That would be S of t. Now what about 12 feet per second? So that is how that is the velocity of the package, right? The velocity of the package. The package is just about to be dropped. So when the package is dropped, this is the speed of the balloon. So the velocity in terms of the balloon would be that, but then we are talking about the velocity in terms of the package. And so at the time when the package is dropped, that will be 0, right? So then v of t in this case will be v of 0, and v of 0 is given to be 12. So we have all these details we can collect. And so I want to come down here and put together all that I have. So first, the differential, we need these two things, right? Differential equation and the initial value. So differential equation is this dv over dt, which is negative 32, and the initial condition is the velocity when the package was dropped at time 0. Then over time it falls to the ground, but when it is dropped it is time 0, so v of 0 is given to be 12, and this is when the balloon is initially rising. I'll just say that. When the balloon is rising, that's when the package is dropped, so they match there. Alright, so now we need to solve the differential equation. When we say solve, we actually are trying to find its antiderivative. So dv over dt is negative 32. So antiderivative will be v, basically v of t. So here we know that this is like, this is t, right? There's no x here, but it's t. That would be t power 0. So it's like n is 0. So that will be negative 32, 1 over 0 plus 1, t power 0 plus 1, and of course a plus c. v of t is negative 32 t plus c. That's your velocity. And now we use the initial value, which is v of 0 equals 12. And we do know that this is your x. I'm sorry, in this case it's t. I'm so fixed on x myself. So this is t, and this is v. So let's plug in for t and v. So v is 12 equals negative 32 times 0 plus c. So this implies your c is 12 because that's a 0, makes it a lot easier. And this back in turn implies v of t is negative 32t plus 12. And this is nothing but what they basically asked us, which is how long does it take for the package to reach the ground. So we now have the velocity. We found the velocity. How long will be the time? So this will be the velocity of the package. This is going to be super interesting because now this velocity, from here we need to find the derivative again so that we could find the height And then from the height, setting the height to 0, we can find the time t. So we are 2 layers away. So we wanted to come down to the s, but we had a of t, acceleration due to gravity. From that we got velocity, and from velocity we're going to get our position, s of t. This is going to be interesting. So, you know, v of t is the same as ds over dt. Right? It's the derivative of the position. So that's negative 32t plus 12. So you need to take the antiderivative. So it is a double iteration process. Antiderivative of this would be s, which is negative 32. Keep that as it is. Quickly right here. This will be n is 1, and here t power 0. So 1 over 1 plus 1, t power 1 plus 1, plus 12 times 1 over 0 plus 1, t power 0 plus 1, and of course plus c. Negative 32 times 1 over 2t squared plus 12t plus c. Simplify this, so you get s equals negative 16 t squared plus 12t plus c. So how do we find the c here? Because there we got the v and the t. The initial value for v was v of 0 equals what was it? V of 0 equals 12 feet per second. So I want to take you back to the question quickly. Okay, do you see any other hint? We used the 12. We didn't use the 80. What is the 80? 80 is the height of the balloon from the ground when the package is dropped. So the package is dropped from a height of 80. So when we begin clocking the time as to how long it takes for the package to reach the ground, when we begin clocking the time is 0. And at time 0, the height of the package is 80. That's what this means. So I'm going to come down here, say at time 0, the height of the package was 80 feet. I'm just writing it out here, and I'm going to put this as, or I'll just write initial value was that s of 0, time is 0, was 80 feet. So s of 0 is 80. And we can use that where t is 0 and s is 80. And back here, plug in s as 80 equals negative 16 times 0, that's 0, calculate, plus c. And what we have is that c equals 80. So come back and then say, I say s, but it's actually s of t, so let's put s of t equals negative 16t squared plus 12t plus 80. Wow, so we started from a of t, acceleration, we came down to v of t, from v of t we came down to s of t. We've got this. We're not done yet, because they want to find the time it takes for the package to reach the ground. The package will reach the ground when the height is 0, when s of t is equal to 0. Height is 0. So it's complete reasoning out, where you realize that I can build an equation like this, where I can set the s of t to 0. Again, we've seen these kind of problems. It's a question of putting them all together in this kind of sequence. So you set this equation to 0. I would say pull out the GCF, and then, in fact, 4 would work for GCF, so let me do that. 4, pulled out a 4, you get negative 4t squared plus 3t plus 20 equals 0. And then for this one, use the quadratic equation. Quadratic formula. This is a quadratic equation. Use the quadratic formula, and that will give us t is negative 3 plus or minus negative b plus or minus b squared minus 4ac all over 2a. Of course, I will let you do the algebra part and use your calculator because we are trying to find the time, and we want it to be in decimals. So we get negative 1.89 as one of the answers, and we get all these approximate answers. So we put approximation symbol here, and this is approximately 2.64. We have two answers because it's a quadratic, so you do expect two solutions. Thankfully, for the physical meaning of time, we cannot accept negative root, and so we can say the package hits the ground. About 2.64 seconds. Remember again, the units must be included in your answer after it is dropped from the balloon. I know this was a very unusual problem where you did not see layers of this iterative process, finding the derivative, or the antiderivative I should say, but this was very interesting. So now let's move on to the last concept in this section. So we technically move to the second part of calculus, integrals, at this point. Because if you recall my very first lecture, I mentioned about the whole, the premise of the study of calculus. It is, it branches into two types, which is derivatives and integrals. So all along we saw derivatives, and you notice that integrals is basically antiderivatives. So derivatives and antiderivatives, that's basically the study here. So the derivatives is what we saw, and here we look at indefinite integrals. And if you look at the definition, you'll know that it's actually your antiderivatives. It says the collection of all antiderivatives of f is called the indefinite integral of f with respect to x, and is denoted by integral f of x dx. The symbol integral and the integrand are being discussed here. So let me write that out here. So you have this this s-like symbol, right? So integral. Think of this, it also looks like an eye, like a decorative eye. So think of that as integral. Okay. So you have to kind of exaggerate it a little bit. It also looks like some kind of a partial music symbol, but it's an integral sign. Then you have f of x. This is the function dx. I love this notation for its simplicity and for the uniqueness here, so we know we can't mix it up with anything else. But what it's really doing for us is that it is replacing all this confusion of capital F of x or the dy over dx setup, which is not confusing, but again, you now have the f and the y and all these things. So we have here f of x, which we've always seen as a regular function. And we took f of x and found its derivative, and we used the f prime notation. Now here we can take that same f of x and throw in the integral sign here, and that means we are asked to find the antiderivative. So that is why I like this notation. This is called the integral sign. So you simply read it as integral, and then that means we need to do that I sign. F of x, this will be the original function, and it's called the integrand. Integrand is anything that goes inside the integral, just like the radicand. Radicand is anything that goes under the radical sign. So that's the name here, integrand. And this dx, x is the variable of integration. And again, this is super important because if you go back to derivatives, we said derive y with respect to x, with respect to which variable really matters. Because if I gave dy over, no, let me say y equals 3 r squared plus 4x squared. Okay, if this is the case, if I said derive y with respect to x, then you're free to treat this r here, which is another variable, as a constant. So that means dy over dx will be 0 plus 4 times 2, 8x. So the answer is 8x. On the other hand, if I said derive y with respect to r, then the x becomes a constant. So then dy over dr, notice how I've changed the denominator. That'll be 6r plus 0, which is 6r. So you can clearly see that the denominator makes all the difference, because we really need to know how fast is y changing with respect to the x or with respect to the r, and that can change the whole meaning of it. And so the variable of integration is super important for us to know what we are deriving, or in this case, what are we anti-deriving for the function. Okay, so your integral is basically another name to unify all the antiderivatives that we have, because you know how we have that plus c. So it's like the collection of everything. It's a combination of all the possibilities of all antiderivatives, and it's all kind of collected under this. We will look in chapter 5 as to how it also is meaningful in terms of area. We'll get to that, because again, if you recall my very first lecture, I spoke about these two problems. How do we find the slope of a curve? And calculus answers that question. Calculus also helps us answer the question, how do we find the area under a curve? And so we will see how the antiderivatives will also be helpful in answering that part of the question. Okay, so integral is the name now for antiderivatives. But why indefinite integrals? Again, there is something called definite integrals that we will look at in chapter 5, and therefore this is called indefinite. Definite integrals, as the name says, it's definite, so it goes from a to b. So if you had an interval over which this is defined, it's definite integral because it's defined over it. Because we didn't give you any interval here, because it's a collection of all antiderivatives, there is no interval, and therefore the indefinite integral. Given the change in notation, a problem that reads as find the antiderivative of, say, f of x equals 2x, or it could say, give it to you as a differential equation, dy over dx is 2x. If it came in any one of these forms, can be restated as simply evaluate integral 2x dx. You see how the dx would be a differential if you throw the dx on the other side, and that's basically what we're doing. We're saying this is dy is integral 2x dx, so find y. But all that is kind of encapsulated here when they simply say evaluate. So the difference in these notations, f of x or dy over dx, is removed in the sense of using the integral, the indefinite integral, and this implies the answer will be x squared plus c, because no matter which notation we used, the answer should be the same because they're all antiderivatives. Likewise, we could say, integral of cosine x dx. That will be your sine x plus c, because k is 1, so 1 over 1 sine 1 x would be the sine x. So let's do a couple of problems now in this type. Evaluate integral x squared minus 2x plus 5 dx. See how crisp and concise it is? We're basically finding the antiderivative, so go ahead and understand that here n is 2 minus 1 minus 0, and it's all the power rule that we're using. the reverse of this. So we now have 1 over 2 plus 1 x power 2 plus 1 minus 2 times 1 over 1 plus 1 x power 1 plus 1 plus 5 times 1 over 0 plus 1 x power 0 plus 1, of course the plus c. So we have this. So it's 1 over 3 x cubed minus 2 times 1 over 2 x squared plus 5 times x plus c. The 2's will cancel off. So that's x cubed over 3 minus x squared plus 5x plus c. This would be our answer, right? Now I'd like to also kind of consider how you could use the linearity property, right? Antiderivatives are linear, so you could also see this as, let me write the question first, as a split of individual terms, right? Sum and the difference rule. So then you can pull out the constant, just like we would do the derivative. It'll be a whole lot easier where you can just focus on the x and pull out the constants. Plus 5 integral dx. And that again would be x cubed over 3 plus c. There's going to be many c's, so I'm going to call this c1 minus 2 times x squared over 2 plus c2 plus 5 times x plus c3. But notice c1, c2, c3, if you combine all of these, you'll get another constant, isn't it? Because you combine all the constants, you're going to get another constant. I might as well call it a c. And so we can rewrite this simply as just the terms first, x cubed. Oh, here again the 2's will cancel off, so I'll just write that as minus x squared plus 5x. And all the c's combined will be one common c, which was what we got up here. Okay? So you can see them individually to be written out as separate c's, or you can just attach a c in the end. They're all equivalent. Let's try this one. Now notice that the variable of integration is t, so everything is with respect to t. And without having to explain it in too many words, that's just that dt there makes it a whole lot easier for us to know what to differentiate with respect to. In this case, the antiderivative. I'll try to split them up first. One more step where I pull out the constants. And so I have half times t cubed over 3 plus 4 times t power 4 over 4 plus a c, because I know there's a c1 and a c2, which will combine to give me a constant. So that will be t cubed over 6. The 4's cancel off, gives us t power 4 plus c. Negative 5 over 4 dx. Not a problem. Plus the c. So 1 over negative 1 over 4. The problem was not really difficult. It's a question of cleaning up your answer. So this 4 goes on top with a negative, and that x will come down. You can write it like this, or sometimes you could be asked to write it as the 4th root of x plus c. integrate. Now if you have something like this, again use algebra. Always remember algebra before calculus. So use algebra, which means you just repeat the step but separate the terms. And we know that because of the law of exponents, we can simplify all of these. Okay? There are many ways to simplify it, but what I'm trying to do here is write all of them as a power. And this t squared, I'm bringing it up, is -2 plus t power half times t power -2. I hope you can see what I'm trying to do, because law of exponents allows you to add up the powers. Okay? That basically becomes t power -12 plus t power -3/2. Use the LCD when you're adding fractions like that. This is all still the same problem, meaning we didn't really begin to do the integration. We didn't find the antiderivative yet. So now I'm splitting them up. And this is now the time for us to plug in use the formula. Plus C. Clean up. That gives us, it's a positive half, so it's going to be a 2, t power half, and that will be a negative that's going to be 2 square root of t minus 2 over square root of t plus c, and that will be your answer there. Let's try trick problems. Not trick, trig problems. Here the integral has 3 cosine 5 theta, and the variable of integration is theta. So the process of finding the antiderivative is called integration. So if you find me using the word integration, all I mean is finding the antiderivative. I pull out the 3 cosine 5 theta d theta, and that 3 is 5 here. You have to go back to the table to make a quick reference. It's way far back, so I'm not going to scroll out to that. You can check this out in your ebook, or if you've been taking notes while I was doing this, that will be helpful too. You can reference your notes on these formulas. Actually, it's a good idea each time I show you a formula or a theorem, if you can take notes on them, it'll be easy for you to make a quick reference in your notebook, especially during those times when I don't scroll back to show you that. 1 over 5 sine 5 theta. That's it. So that's going to be 3 over 5. Shove them all together always. Don't just leave them hanging like that. Okay, we'll do something else. It's a little different. So I'm pulling out the half, and I'd like to split this up. Into 2 separate integrals. Looks like I'm having a hard time writing the cosecant. Okay. Now the formula itself has cosecant squared. So the formula itself is to help you find the antiderivative for cosecant squared x. So you don't try to undo the square or anything. Just apply the formula that we know. That would be negative cotangent x minus integral or antiderivative of cosecant x cotangent x itself is a negative cosecant x. So there is a negative in the expression and there is a negative in the formula. Please watch out for that. And then there is a plus c. That's all happening outside the half times this. So that will be negative cotangent x over 2 plus cosecant x over 2 plus c. I suppose the next one will be a little more interesting. Evaluate integral cotangent squared x dx. So go back to see if the formula has a cotangent squared x. Okay, unfortunately, we don't have that. We the list of formulas actually has, in fact, nothing for cotangent. We have secant squared, cosecant squared, secant kx tan kx, cosecant kx, cotangent kx, but we don't have anything for cotangent, let alone cotangent squared x. So what do? So I'll just say, since there is no direct formula, and because this is trig, right, we will use trig identities. To simplify. If it was algebraic expression that was not directly helpful, then we have to use algebra techniques to simplify. But here, because it's trig, we have to use the trig techniques, and usually we use the identities. So we have this identity which says, because this involves a square, so the first thing that comes to my mind is the Pythagorean identity. Cosecant squared x is 1 plus cotangent squared x, and we also know that cosecant squared x has a formula, but not the cotangent squared x. So if I can rewrite this whole thing that has cosecant instead of cotangent, that will be a lot helpful, isn't it? So this implies cotangent squared x will be cosecant squared x minus 1. And now you take the integral. So integral of cotangent squared x dx will be the same as you took the replace the cotangent squared x with cosecant squared x minus 1. And then it's a breeze, because you have to separate them into two individual integrals, and we know that integral of cosecant squared x, so in other words, the derivative, antiderivative of cosecant squared x is available to us. That would be negative cotangent x, and this integral of dx is minus x itself plus c. Again, cosecant squared kx is what the function, or the formula, gives us. So here k is 1, so it looks a lot simpler. And that is how you handle questions that do not directly have formulas. Root 2 minus 1 dx. Again, don't be stumped because you have the root 2 and all that. You just have to see if it's a constant. Root 2 minus 1 is a constant, right? Root 2 is 1.414. That minus 1 will give you 0.414. So it is a regular number. So don't be again worried about that. You go ahead and use the formula. But just that, remember, here your n is root 2 minus 1. So remember to add 1 to it when you apply the formula. So that will be 1 over root 2 minus 1 plus 1, x power root 2 minus 1 plus 1, n plus 1. Right? And that is just a step away where it's 1 over root 2 x power root 2 plus c. We're kind of done, but I just wanted to squeeze in maybe just a couple of initial value problems. So I'll just say solve the initial value problems. So the first one, only because I wanted to use some trig or some double antiderivative kind of problems. So bear with me here. 1 plus cosine t s of 0 equals 4. So if you had something like this, if you recall, this was the differential equation. So we need to find the antiderivative. It's the notation change, but we've been doing the same thing all along, with be it the integral sign with the I-like sign, or the it also looks like an S, right? The antiderivative version doesn't matter, because antiderivative of ds over dt is just the S. And so 1 0, and here k is 1. That will be t plus 1 over 1, 0 plus 1, right? All that. So I'm going to skip all that because we've been doing a lot of those types. So it's going to be what? T plus sine t plus c. So s of 0, and each time I used to write initial value and then mark this as x. In this case, this will be t, and this will be s. So we can also kind of write this in a crisper form, where I say t is equal to 0. When t is 0, for the position would be 0 plus sine 0 plus c equals 4, because that's our initial value. S is 4. And that helps us to find c as 4. We come back and say s of t is t plus sine t plus 4. So we've seen this. Do another one. dv over dt is 8t plus cosecant squared t, and v of pi over 2 is given to be negative 7. So we're going to practice using the crisp notation. So I'm going to, not give too much of an explanation. So I want you to just watch me do this. T is pi over 2. Solve for C. And that will be your answer. So don't be always expecting a nice round number for C. And here it involved pi squared. Totally fine, because pi is an irrational number. d squared s over dt squared is given to be 3t over 8. ds over dt when t is 4 is given to be 3 and S of 4 is given to be 4. You see the second derivative there? It recalls our balloon problem where the package was dropped, because the second derivative actually indicates the acceleration. So we got that. So when you see the second derivative and you see the S of 4, that condition, you know we're going all the way down, 2 layers down to S of t from the second derivative. So let's start here. The derivative, antiderivative of d squared s over dt squared is one derivative below, so it's ds over dt. Use the initial value. It's given to be 3. So 3 minus 3, so actually C is 0. So come back here and say ds over dt is 3 over 16t squared itself. Now we go one more layer, one more step of antiderivative. The antiderivative of ds over dt is simply ds, 3 over 16. There's another c that comes here. If it's confusing, you can put c1, c2. I don't find it confusing, so I got that. So the 3 and the 3 will cancel, so I have 2 cubed over 16 plus c. Now we are given s of 4 equals 4. So to use that crisp notation, I'll say that t is 4. This is also, the whole equation is equal to 4. So 4 cubed over 16 will be a 4. So 4 cubed is 64. Oh, once again, c comes out to be 0. So your s t will be t cubed over 16 itself. And that's what we want to find. So class, we saw a number of problems and different problem types as well. I hope this was very useful to you. And with this, we come to the end of chapter 4. I will see you in the next lecture, starting chapter 5.